So this is an introduction to what are called logarithmic functions, and it turns out that logarithmic functions and exponential functions are related to each other. I will tell you right now, they're inverses of each other. But there's another way to look at a logarithm as opposed to an exponent, and that's to take a logarithmic expression and write it as an exponential expression. And what I'm talking about here, I really believe that this analogy is useful, is writing something in one language in a different language. So for example, if you are bilingual with English and French, and you've been thinking English all day and somebody says bonjour to you, you still know they mean hello. Is that right? Bonjour is hello? I think it is, yeah. And if you're thinking French all day and somebody says oui, you know, even though you might want to convert it to English, you know what that means. It means yes. So you have to think of logarithmic expressions and exponential expressions as potentially meaning the same thing. They're just rearranged differently. They're in a different language. Excuse me. And then we're going to be evaluating logarithmic expressions based on what the meaning of a logarithm is. So to begin with, what a logarithmic function is the inverse of an exponential function. And the word inverse here is the same as the inverse we talked about in chapter 1. The inverse of a function or the inverse of an equation involves taking the x and the y and switching them. So for example, if I have a function y equals 2x minus 6, and I rearrange that function, I switch x and y, what I end up with is x equals 2y minus 6. Now when you look at the equation on the right, everybody, that function, x equals 2y minus 6, which is the inverse of the function on the left, is not written in kind of a standard form. What we always want to do is write functions as y equals. And you have all developed the skills over a fairly long time, but you should have the skills necessary for knowing how to rearrange that for y. What you would do is you would add 6 to both sides and divide by 2. So that's really a piece of cake. You're going to have x minus 6 all over 2. If you divide x by 2, you get a half x. If you divide 6 by 2, you get 3. All right. I am reviewing what inverses are for a number of reasons. Another example would be y equals x squared. Well, the inverse of y equals x squared is x equals y squared. And there was a time where you believed you knew everything there was to know about square roots and squares, and you were taught that squaring and square rooting are opposite operations, so they're inverse operations. But you would have said, oh, well, that's easy, x equals root y. Y equals root x. But then, because the math got more complicated, it was demonstrated to you that there are other numbers you can square to get x, square to get x, other than the square root of x. You can square the negative square root of x, and that would give you y squared. So the bottom line is you were taught some new language here. Specifically that when you take the square root, you say plus or minus root. And that's what the function is. Now it's a bit of a lie because this thing that I'm going to highlight is not a function. And it's not a function because it has two pieces. It has y equals positive root x, which looks like this. And it has y equals negative root x, which looks like that. So the entire thing is not a function. But you rearrange the equation for y. That's the bottom line. And that's called a square root function. So a quadratic function and a square root function are inverses of each other. So now let's look at the exponential function y equals 2 raised to the power of x. That exponential function is on the left-hand side of the screen that you're looking at right now. And if I switch x and y, I get what's called a logarithmic function. And the logarithmic function is x equals 2 to the y. And we could, split hairs here and be really picky and say, you know what, that logarithmic function is an exponential function too, of some kind. It's an exponential relationship. It's just that x is no longer the exponent, so we call it logarithmic. I really want to highlight for you because something's going to happen in about 5-10 minutes that may cause confusion. I really want to highlight to you that these two functions are different. These two functions are not the same function. And you might be sitting there going, well, I know they're not. Well, something's going to happen, as I said, that might cause confusion on that front. These are inverses of each other. Now, the question becomes, how do you rearrange x, that's a horrible color, how do you rearrange x equals 2 to the y? And I know that you've got the notes in front of you, but just paying attention up here, if I wanted to have a little bit of a good laugh and kind of mess with you, I could say, okay, everybody, we've got x equals 2 to the y. I'm going to give you a minute to rearrange that for y. And you can't. You can't rearrange that for y any more than a grade 3 student can rearrange this for y. Even assuming a grade 3 student understands what this means, they haven't been taught the square root symbol yet. That's a concept that's foreign to them. So you haven't been taught the symbol, the symbolic language that will allow you to write y equals. Well, it turns out you write this. And now we're going back to the notes. It turns out that when you rearrange x equals 2 to the y, for y, you get that expression. And that expression is pronounced y equals log base 2 of x, or y equals the base 2 logarithm of x. And all it means is, this is really crucial, that y, all it means is that y is the exponent to which you raise 2 to get x. And if you look up here, y is the exponent that you raise 2 to get x. So, what I now have for you is this statement, and I'm telling you these two things are the same. This is going to take a little bit of practice. I'm telling you that if I said x equals 2 to the y, and you said y equals log base 2 of x, they are exactly the same, much in the same way that if I said x equals 7y, and you said y equals 1 over 7 times x, they're the same thing. This is a rearrangement for y of this. This is a rearrangement of y for y of that. So we're going to have to get used to this language. It doesn't matter, I'm going to come back to that in a second. It doesn't matter, I guess I don't have it, what those letters are. If I had the following, and we'll get some practice with this in a bit, but if I had a equals 3 to the r, and you wanted to write it in logarithmic form, you would say r is the exponent to which you raise 3 to get a. And this is the language thing I was talking about. We have to be able to convert from one of these to the other. They mean the exact same thing. Now, there are some things we have to be aware of with this logarithm concept. So a logarithmic function is y equals log base c of x, and then it has all this crap. Look at all this stuff. It has x must be greater than 0. Let's talk about that for a second. if x must be greater than 0, and I know that this is difficult, if I have y equals log base, I will say 2 of x. Why does x have to be greater than 0? Well, if I write that in exponential form, it becomes 2 raised to the y equals x. I would like everybody to ponder, to roll around in your brain how I converted this to this, which are the same thing. And I'm asking you to do that because everybody is going to formulate a way or a pattern to do it. I'm not going to ask for any feedback here. I'm just asking you to think about it. So now let's get back to the x is greater than 0. X, look at what x is. X is 2 to the y. You cannot take the number 2 and raise it to any number and get a negative. You will always get a positive result for 2 to the y. 2 to the 0 is 1, it's positive. 2 to the 10 is a big number, it's positive. 2 to the negative 3 is 1/8, it's positive. So the argument on a logarithm must always be greater than 0. You cannot take the logarithm of 0, and you cannot take the logarithm of a negative. What's something else we're told here? We're told that c must be greater than 0, and c cannot be 0. Well, if you were to go back and look at the base for an exponential function, we said that this base can be a number between 0 and 1 or greater than 1. You cannot have a base that is 0, you cannot have a base that is negative, and you cannot have a base that is positive. So all of this stuff that I've highlighted here in yellow, we can kind of ignore it, but we should understand that it's there for a reason. One other note here, the textbook uses C for the base and your formula sheet uses B. I want to pause for a second here and make sure you understand this view that you're looking at, that y equals 2 to the x and x equals 2 to the y are inverses of each other. And added to that, x equals 2 to the y is the same. This is the same as y equals log base 2 of x. And what that means, and this is where you can easily be confused because you might think we're going in circles here and we're not. That means that this and this are inverses of each other. Y equals 2 to the x is the inverse of the function y equals log base 2 of x. So a logarithmic function y equals log base c of x is the inverse of the exponential function y equals c to the x. I don't know what kind of questions you might have at this point, but I do want to pause there. Does anybody have any questions so far? All right, so let's jump into the first example. We want to graph y equals 2 to the x and y equals log base 2 of x on the same set of axes. Well, these are inverses of each other. So if we know how to graph 2 to the x, we ought to be able to graph log base 2 of x. I'm not going to use the table of values that I have here. I'm simply going to use what I've taught you already, that for y equals 2 to the x, which I will do in red, the y-intercept is 1. And every time we go 1 to the right, y gets doubled because the base is 2. So doubling 1 gives us 2, doubling 2 gives you 4, doubling 4 gives you 8. You could certainly make a table of values. Going in the opposite direction, I would have to take 1 and divide it by 2. We do know, however, in addition, there is an asymptote, because no matter how many times we cut that y coordinate in half going to the left, we will never reach 0. What does y equals 2 to the x look like? Well, you should already know this, but it looks like the following. And it's asymptotic. That's actually a word. I looked it up one time. It's asymptotic to negative infinity against the x-axis. So all we have to do now is switch everything about x and y to get the logarithmic function. So I am going to use blue for y equals log base 2 of x. And I'll label these graphs in a bit on the actual grid. Well, if 2 raised to the x has a horizontal asymptote, then y equals log base 2 of x will have a vertical asymptote because they are inverses of each other. If the horizontal asymptote is the x-axis, that means the vertical asymptote on the inverse function will be the y-axis. We can go ahead now and start picking individual points, like this point, which is at 0, 1. Well, if I swap 0, 1, I get 1, 0. This point is at -1. I'll just write this down so you can see it. This point is at -1, 1/2. So when I swap those numbers, it's going to be at 1/2, -1. This point is at 1, 2. Swapping the numbers gives 2, 1. 3, 4 is the next one. Swap the numbers. 2, 4 is the next one. Swap the numbers. 4 becomes the x coordinate. 2, 4 is the red one. 4, 2 is the blue. The last one, which is up here that I'm pointing at, is 3, 8. So I swap that and it becomes 8, 3. And you can see that we get a nice reflection across the line y equals x. Right, here's y equals x. Well, close enough. So that's what the graph looks like. I will warn you right now that there will come a time, maybe even today, where you learn how to graph y equals log base 2 of x on your calculator, and it looks like crap. It doesn't look like what it should look like, okay? So this is one case where I want to tell you your graphing calculator is very deceptive. I forgot a little arrow down here. It continues down to negative infinity. The red graph, of course, is y equals 2 to the x. So before we get to the details of these graphs, does anybody have any questions with regards to getting the graphs? All right. Complete the following table to compare the graphs of the functions. So you have them in front of you. I don't want to set up multiple monitors so I can look at this. When you take a look at the graph that's red, that I graphed in red, the 2 to the x, the domain is x is any real number. The range is y is greater than 0. We knew this yesterday, the day before maybe even. There is no x-intercept, and the y-intercept is at 0, 1. The asymptote is the x-axis, which is the line y equals 0. Now, I shouldn't need to refer to the blue graph to determine all of the same information for log base 2 of x equals y, because these two functions are inverses. I really can't stress that enough today. This is the inverse of this. And what that means is that whatever was true about x becomes true about y. And sure enough, if you look up at your y equals log base 2 of x graph, it goes up and down forever. So y is any real number. But when you take a look at the domain of that graph, it's always to the right of the y-axis. So what was true about y becomes true about x. If there's no x-intercept on y equals 2 to the x, there will be no y-intercept on y equals log base 2 of x. And you can look at the graph and confirm that. If the y-intercept was 1 on y equals 2 to the x, then the x-intercept will be 1 on y equals log base 2 of x. And there will be a vertical asymptote, that's the y-axis, whose equation is x equals 0. Now, does anybody have any questions? All right, what we're going to end up doing either later today or tomorrow, things are going pretty good, so we might do 2 lessons today, but we'll see, is talk about transformations of those. But in the meantime, what we want to do is concentrate on the meaning of a logarithm in terms of converting from one form to the other. And I don't know where I picked this up. I don't think it's in your textbook. I think it was some teacher I was talking to one time, and they explained this to me, and I went, wow, what a useful idea. What a logarithm is an exponent, okay? And I'm going to keep coming back to that whenever necessary. So the things I'm highlighting here are the same as each other. Y equals c to the x, which I'm underlining in blue. Y equals c to the x is the same as saying x equals log base c of y. So I want you to focus, everybody, on the expression I underlined in blue. I want everybody to really focus on this expression, okay? What is the exponent in that expression? The exponent is x. Now I want you to look at the other expression, which is equal to it. What is x in the pink expression equal to? It's equal to the logarithm. So the exponent is the logarithm. The logarithm is the exponent. Log base c of y is a logarithm. What's it equal to? It's equal to x, which is the exponent to which you raise c to get y. So those two ones that are highlighted in the middle with yellow are identical, and let's try something different. And these two orangey kind of ones that are highlighted are the same as well. And when you take a look at the very bottom equation, y is the exponent. Y is the exponent. When you take a look at what y is equal to the logarithm. So the exponent is the logarithm. The logarithm is the exponent. These things are the same above the brownish line, and the things below the brownish line are the same. And I hope with a little bit of thought, I'm talking and asking you to think at the same time, which isn't ideal, but with a little bit of thought, I hope you understand that there's nothing special about the letters X and Y. They could be anything. So for example, and I've mentioned this in my math classes to you before, everything we write on paper is just a squiggle that's meant to represent something. So if I said that duck was equal to fish raised to the moose, and we wanted to write that in exponential form, Well, moose is the exponent, so moose is equal to the logarithm. And the base of the exponential expression is fish, so that's the base of the logarithmic expression. Another way you can look at this, and I will make up one last example before we get to the official examples. Another way you can look at this is to say if a equals b to the c is the same as c equals log base b of a, and I admit this comes naturally to me. But if those two things are the same, then what some students do is the following. They say the base is the same in both, right? Whatever the base is, that's the base whether it's exponential or logarithmic. In one of these, there is something that is by itself. In the exponential one, a is by itself, but a is not by itself in the other. In the logarithmic one, c is by itself, c is by itself, but c is not by itself in the other. I guess what I'm saying is you have to come up with some kind of rule to convert these around. Now, before we get to the examples and doing these, which may not take very long, does anybody have any questions? All right. So convert each of the following from exponential form to logarithmic form. Well, this is how I do it. P is the exponent, which means P is equal to the logarithm. It's the log base 4 because the exponential form had a base 4, and it's of n. And I'm going to be saying this over and over and over again. When you look at this, I can say P equals log base 4 of n. But what I will say a lot of the time is P, and I'm looking here. I'm not looking at this. I look at that and say P is the exponent to which I raise 4 to get n. That's what P equals log base 4 of n means. And that way when I get to B, I say negative 5 is the exponent to which I raise 2 to get 1 over 32. Logarithms can be negative. Logarithms can give you a negative exponent. You can't take the log of a negative, though. Any questions with A or B? All right, well, that's good. Let's take a look at 3a, convert to exponential form. Well, 2, see, I'm sorry, this is just how I think, and I think it's useful. I look at that and I say 2 is the exponent to which you raise 10 to get 100. It just kind of flows. Once you get in the idea that the logarithm is the exponent, and the logarithm is 2, then 2 is the exponent to which you raise the base. M is the exponent to which you raise x to get k. And with C, you can't convert it from one language to the other when there is a coefficient. So what we can do to begin with is divide both sides by 4 and get log base b of 9 is equal to 4. So 4 is the exponent to which I raise b to get 9. Incidentally, I don't know why this thought entered my head, but I better address it now. If I had log base 3 of 12 over 4, you can't cancel anything. You can't, cancel the 12 over the 4. That 12 is locked in with the logarithm. It's not a factor. Any questions with 3a, b, or c? All right. What is log base b of 1? Now things start to get a little more abstract. So in my mind, and I will write something down for you in a second, but log base b of 1 is asking me for the exponent to which I raise b to get 1. Now what we could do if we wanted to is we could say, let's call this A for answer to the question. We want to know what that's equal to. And then we can write it in exponential form. A is the exponent to which we raise the base to get 1. The question becomes, what exponent do we raise b to get 1? 0. B to the 0 is 1. So A is equal to 0. And there's not a lot of work there. There's no algebraic justification. It's a fact. It's like saying, what's 2 times 3? It's 6. What's log base b of 1? It's 0, because 0 is the exponent to which you raise b to get 1. With that in mind, what's our answer in B? I don't want anybody to type anything in the message window. I just want everybody to think about what I've told you about logarithms so far. And in the message window, if you know what the answer to B is, if you know what this is equal to, type the word yes. Okay, now you can start typing what it's equal to, and I really hope that I see the same number everywhere from everybody. It is in fact 1. Because this is saying, and I don't know, I don't need to write A, but I will. This is saying b to the A has to give you what you're taking the logarithm of. There's 2 b's here. So this is the interpretation. So you're saying, to what exponent do I raise b to get b? Well, you raise it to the 1. The answer is 1. Log base 12 of 12 is 1. Log base 8 of 8 is 1. Log base 0.5 of 0.5 is 1. I would like everybody to think, and I got to redo my notes. I really ought to have some brackets there. I would like everybody to figure out what log base b of b to the n is equal to. And type yes if you know. And please don't type the answer. And if you get this one right away, and you're looking at why everybody else doesn't get it right away, that's because everybody else is hitting a little bit of a wall here. What's obvious to some people is not at all obvious to everybody. So let me describe to you how I view that question. Maybe, that's good. Yes, question mark. We're a little apprehensive here. Let me read how I read that in my brain. Log base b of b to the n, even how I said that, log base b of b to the n, is saying, what exponent would I raise b to get b to the n? What do I raise b to so that it becomes b to the n? Well, n. And this is not obvious. The answer here is n. We're saying b raised to some exponent that we have to find is equal to the argument of the logarithm which is b to the n. So what do I put here to make this a true statement? Well, I put n there. So log base b of b to the n is n. Let me demonstrate this to you with a slightly different example. If I said to you, what is log base 2 of 2 to the 6? Okay. Can everybody please figure out what 2 to the 6 is? And you can type it in the window if you like, in the message board. 64, right? 2 times 2 times 2 times 2 times 2 times 2. It's 64. So now we have log base 2 of 64. Now, if you really get what's going on here, you'll either be chuckling verbally or in your brain at this next question. I want everybody to use your calculator and find out the exponent to which you raise 2 to get 64. What do you raise 2 as a power of to get 64? Be very careful here. I'm asking 2 raised to what gives you 64? It's 6, right? Because that's how we got 64. We said it's 2 to the 6. So if this is 6, why did we bother raising 2 to the 6 and then undoing it? This further exemplifies the idea, everybody, that exponential and logarithmic are inverses of each other. They undo each other. All right, let's move on. Let's take a look at log base 2. Oh, okay, I didn't know that was going to happen. This is 6. And you're not really showing any work here. You're simply saying, to what do I raise 2 to get 64? Now, I am curious. How many of you think you know the answer to E? Type yes if you think you know the answer to E. There will be a few, and they're probably right. But there will be very few usually. So now the advice I'm going to give everybody is the following. If you see something in mathematics dealing with logarithms and exponents, and it's in logarithmic form and you don't know the answer, or you don't know where to go, change it to the other language. So we can say this is equal to A stands for answer, and if I write this in exponential form, I get 6 raised to the A equals 1 over 36. And now what I have, everybody, is a question that's an exponential equation where we're going to convert to the same base. I can write 36 in base 6 as 6 squared. And since I have 6 to the 2 on the bottom, I can write 1 over 6 to the 2 is 6 to the negative 2. That's how we use negative exponents here. And I'm assuming that, how many of you people that typed yes knew the answer was negative 2? You know, and that it may be that you suspected it was negative 2. You weren't sure, but that intuition was right. Because if 6 to the A equals 6 to the negative 2, then A must be negative 2. That's our answer. All right, how many of you, by typing yes, believe you know what log base 8 of 2 is? That's trickier. All right, so Aiden's the only person who thinks he knows, so a lot of pressure here, Aiden. What do you think it's equal to? It is 1/3. Now, fewer people will intuitively know this is 1/3. Why is it 1/3? Well, if you don't understand something that's a logarithm, write it in exponential form. Now, I don't believe, Aiden, this is what you did. Did you just say to yourself you have to take the cube root of 8 to get 2? So 2 to the 3 is 8. Oh, I see. So it's kind of an opposite, twisted around operation. See, I'll come back to that in a second. So if I convert this to exponential form, of course I have to introduce this other thing, the answer. Then I say, how do I solve this? Well, I can write this as a common base. 8 is 2 cubed. And now I have on the 2 a power of a power. So I multiply those two exponents and get 2 to the 3a equals 2 to the 1. I really like that color. And that means that 3a is going to be equal to 1. So a is 1/3. See, what you could have said as well, is that this is 1/3 because log base 8 of 2 is saying to what exponent do I raise 8 to get 2, which is what I have here, right? And I know that the cube root of 8 is 2, and cube root is the equivalent of raising something to 1/3. All right, let's take a look at example 5. If you do not see a base, then the base is 10. This is called a common logarithm. Base 10 is a common logarithm. And it's common because we use a base 10 in our number system. So if you were asked for log of 10,000, that means it's log base 10 of 10,000. And I would like everybody to think, believe me, I'm going to, at every turn, tell you don't rely on your calculator all the time. I would like you to think about the number to which you raise 10 so that you end up with 10,000. I'm asking you to think about what goes here to get 10,000. This is one where you can go ahead and type the number into the window if you know it. That's 4, right? 10 times 10 times 10 times 10. 10 to the power of 4 gives you 10,000. So this is 4. For B, we're asked, this is base 10, right? Sometimes I'll do this. I'll put it in because it's not written there. If it's not written, it is base 10. This is saying 10 raised to some number will give you 0.001. I think fewer people would know this just immediately, but go ahead and type the answer if you believe you do. Yeah, that's -3. 10 to the -3 is equal to 1 over 10 to the 3, or it's equal to a 1 moving the decimal place back 3 places. So this logarithm is equal to a negative. Now, luckily, well, I don't know. Sometimes I feel like I'm the old guy that says, I wish we didn't have calculators and we did everything with pencil and paper, but it turns out that you have a log key on your calculator. It's right there. No. This is tricky. You see where it is, right? So there's a log key, and it just says log. What's interesting is I want you to take a look at your squared key. Do you see the x squared key, I hope? What's the yellow function behind it? Square root, right? That's because the inverse of squaring is square root. Look at your sine key. What's the yellow function behind it? Well, it's the inverse sine. Look at your log key. What's the inverse operation? 10 to the x. So we could have said that log of 10,000, and my high school math teacher would be appalled that we have to use a calculator to determine it's 4. We could have said the base 10 logarithm of 0.001 is -3. But that's all you have access to essentially as a base 10 logarithm. I'm lying to you a little bit, but I don't want to go any further than that today. Let's take a look at the next question. Estimate each of the following. So we can't use a calculator here because we don't have a log base 3 key. And even if we did, I don't want you to do it that way. This is saying, to what exponent do I raise 3 to get 50? So how can we estimate that? Well, 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, 3 to the 4 is 81. Well, 50 is someplace in between here. 50 is somewhere between 72 and 81. So that must mean the exponent must be somewhere between 3 and 4. And we're back to that thing we were doing yesterday of saying, well, maybe it's 3 raised to the 3.5. Too big. No, not quite big enough. 3 raised to the 3.55. Oh, almost. 3 raised to the 3.57. Let's say 3 raised to the 3.56. 3.56. Just give me 1 second, please. I'll be right back. Just give me a second. It turns out that you will find a way soon, probably tomorrow, where you will be able to determine the exact value. So what I have done, I hid from view what I was doing. I didn't want you to see how I got this, okay? But this is the exact answer. And if I were to take 3 raised to that, you can see I get exactly 50. There is a way on your calculator to determine the exact value of log base 3 of 50. What about log of 250? Well, that's log base 10. So, I don't know, 10 to the 1, that's not even close. 10 to the 2, that's 100. 10 to the 3, that's 1,000. Okay, so it's somewhere between 2 and 3. By the way, exponents and logarithms are very deceptive in how they grow or shrink. I'm going to try 10 raised to the 2.2. I don't know. No, 10 raised to the 2.4. Pretty close to 2.4. Of course, we don't need any special wisdom to find this because we could just go log of 250 because it's a base 10 logarithm. So it's 2.3979. Any questions with example, what I believe was example 6? Okay. Example 7, determine the value of x in each case. Go ahead and type yes if you know the answer to this question just by looking at it, which, by the way, is the goal for everybody. Good to see so many people knowing. I didn't ask you for the answer, but I hope you're all saying it's 3. And the reason for that is when I convert this from logarithmic to exponential form, I get 3 to the x equals 27. Look, everybody, yesterday we learned how to solve equations that could use a common base. Do we really need to formally write 3 to the x equals 3 to the 3 and then x equals 3? No. You look at that and you say 3 is the exponent to which you raise x to get 27, which for those people that immediately knew what the answer was, I really hope that's what you saw and said in your mind or out loud when you looked at that. What exponent do we raise 3 to get 27? Okay, this question is a little bit different. We had one earlier that was similar to this. Go ahead and type yes if you believe you know the answer to this question. And you can go ahead and start typing what you believe the answer to be. Yeah, it is 1/3. This was exactly the same idea as what I believe was log base 8 of 2. 8 to an exponent equals 2. That exponent was 1/3. If you want, you can do this formally by writing it first of all in exponential form, then saying that 27 is 3 to the 3, then multiplying your exponents, then equating the exponents, and dividing by 3 to get 1/3. We want to be careful here because on a written response you have to show and explain steps and do your work. I don't think this requires any real explanation, but the more complicated they get, the more explanations will be required. Go ahead and just type the answer if you know the answer to this. Yeah, it's definitely 3. This is saying x to the 4 is equal to 81. But I have a question for you guys. All of you that said, well, I know x is 3, I'm really guessing that you looked at this, this went into your brain through the receptors in your eyeball, and you said, oh, 3 to the 4 is 81. You probably didn't do any math to get 3. But mathematically, what would you do to both sides of this equation to get x by itself? Well, you would take the 4th root. So x is the 4th root of 81, which is 3. However, instead of doing that, this is going to be helpful later on, don't ask yourself what you do to x to the 4 to get rid of the power of 4 in terms of roots. Ask yourself what exponent you would raise both sides to get x to the 1. And the answer is you'd raise it to the quarter because you have to multiply those two exponents. So 81 to the quarter is your answer. By the way, 81 to the quarter is 3. Log base 5 of x equals 3. Work out what x is, please. And you can go ahead and type it. Yeah, it's 125. You're always converting. Don't understand what this means? And look at it and you're just kind of, I don't know. Write it as 5 to the 3 equals x. That's pretty easy because x is 5 to the 3. So you take 5 to the 3 and you can work out what 5 to the 3 is. It's 5 times 5 times 5, which is 125. Log base 1/2 of 32. Intuitively, how many of you know the answer? Yes or no. No answer is just yes or no. Intuitively, how many of you think you know the answer? It's that question mark again. Yeah, I'm going to end up giving you a tip here that will help you. Aaron, I'm going to put you on the spot here. What do you believe the answer is? No. Did you take 32 squared? Is that what you did, Aaron?
Oh, I think I'm doing it wrong. Sorry. I did something wrong.
Okay. Yeah, it's -5. Aiden's got it. So what you can do if you are looking for a formal approach, which I always recommend, you rewrite this in exponential form, which is a half raised to the x equals 32. And then you say, well, yesterday we learned about common bases. What is the common base of 1/2 and 32? It's 2. I can write 32 as 2 to the 5, and I can write 1/2 as 2 to the -1, and then I multiply the exponents. This was the importance of learning what we learned yesterday. I multiply the exponents, and then I equate the exponents. So -x is equal to 5, which means x is equal to -5. Here is a really interesting rule that you can use. You wouldn't use it on a written response exam. This is the last question, is it? Yeah. You wouldn't use this rule on an exam, but if you want to figure out what log base a of b is, it turns out that that's the same as -1 times log base 1 over a of b. And it turns out that that's -1 times log base a of 1 over b. There's another little rule here. What I am telling you is that if you reciprocate either the base or the argument of a logarithm, then you can multiply the result by -1 and get the same thing. And it will be a few days, well, a couple days before you can appreciate why. We had log base 1/2 of 32. Well, man, I don't want to think about fractions. You know what I'm going to do? I'm going to flip that 1/2 over. Because this, my brain can cope with this. My brain cannot cope with this, but it can cope with that. But Mr. Way said change it to a negative in front. So what is log base 2 of 32? It is the exponent to which you raise 2 to get 32, which is 5. So the answer is -5. If I gave you the following, log base 2 of 1 over 32, you can say that's -1 times log base 2 of 32. It's also -5. If you flip over the argument or you flip over the base, you multiply the logarithm by -1. By the way, I hope what I'm about to write rings true for some of you. This original thing that I have here is equal to log base 1 over a of 1 over b. If, when I reciprocate the base, I multiply the log by -1, and when I reciprocate the argument, I multiply the log by -1, then I guess if I reciprocate both, I multiply the log by -1, and I multiply the log again by -1. Any questions with that last example? Okay, we made really good time here, but I'm still not comfortable with going on to the next lesson today. Well, I don't know. No, let's not. I'm going to burn through the next lesson tomorrow and then do laws of logarithms tomorrow. You have 45 minutes left in class here. I don't think I went too fast, but just give me a too fast, too slow, just right thing. I don't want to do the next lesson today. And you guys seriously have to have faith in me that I'll ensure that you get treated fairly in terms of evaluation. Okay? I'm just not comfortable rushing through something else. I would rather that in the next 45 minutes you get everything done here and you understand it well and you have no questions, and then tomorrow we can start fresh and look at a couple of other things. So a quick review here. These are inverses of each other. Log base 2 of x is the inverse of y equals 2 to the x. That's from your textbook. These mean the exact same thing, though. This is, what you're looking at here is the bulk of what's important for this lesson. And I'll put it back up there in a second. A whole slew of questions for you to work on in the next 45 minutes here.